All right, we're going to be talking about sampling distributions based on means. We've already talked about them a bit based on proportions, so now we're just going to transition to means. Now remember, means are averages. So whereas proportions, we're typically dealing with percentages, like this proportion of the population, like, maybe 5% of the population is under the age of 5. With means, you're dealing with average values, so like average income, average height. This is what we're looking at here. There's some important vocabulary I have up here. The mean of a population is a parameter. Easy way to remember that. P population, P parameter. Mean of the whole population is a parameter, and you typically get that from a census. Other important definition we're going to review here, statistic. The mean of a sample is a statistic. So remember, if we can't perform a census, we can't, get information from everyone in our population, we ask a small subset of that population, which ideally looks like the population, like kind of like a small snapshot, and that will give us a statistic. Now, what I have down here is a sampling distribution based on means. So you figure with a population, you have a parameter out there. Sometimes you know it, most often you don't. But there's a mean for that, population. There's a parameter. We don't typically have it. And then you have all these possible statistics you could get. So we're going to explore some examples today. So anyway, either way, you have a mean, and then you have all these other means you can get. This is the big one. This is the one for the whole population. Typically don't have that, so we get statistics. Now, typically we don't know which statistic we're going to get. So maybe you do a sample, you get this statistic. Not terribly close to your actual population parameter. Maybe you get this one. This one's right on. Now you notice that most of the means here in this sampling distribution, they're pretty darn close to the population parameter here. And we're going to explore, the likelihood of getting those as well as the likelihood of getting something that's really out there. Now you got a few formulas to live by. The mean of all your statistics, like if you did all the statistics, you did a bunch of random samples, ideally the mean of those random samples will give you that population parameter. To find the standard deviation of a sampling distribution, you have the formula here. You take the standard deviation of your population, divide by the square root of your sample size, as long as the 10% condition is met. We'll talk a bit about those conditions too, because it also must be based on a random sample. So we're just going to jump into an example right here, and hopefully this will give you some perspective and maybe take care of any questions you might have. So we're going to start with the average height of U.S. males. In the United States, it is known that the average height of U.S. males is 69 inches. The standard deviation is 3 inches. So that's the population parameter that exists out there. Now, we're going to try and do a random sample of U.S. males. We decide we're going to do a random sample of 36. Why 36? You'll find out. It's a nice, easy number I decided to go with here, but really you could go with any sample size you want. We want it to be a simple random sample. We like random. So first thing we want to do is we want to establish our conditions here. So first condition we're going to check, I always like checking this one first, the random condition. Is this a random sample? Whoops, let me try a different point here. Here we go. Some styluses are better than others, folks. Usually when I use my other stylus, it makes too much noise, so that's why I'm trying this one. All right, random. Is this a random sample? Yes, because I said so. I said it was a simple random sample. You usually want some sort of proof of that. 10% condition. Now you'll remember this from sampling distributions dealing with proportions. You want your sample size, which in this case, 36, to be less than 10% of your entire population. So we're going to go with 1/10 of all U.S. males. I think it's quite safe to say that 36 is less than 10% of all U.S. males. So we're going to say that's met. It's always good to check that condition. You always want to do that. Because if it gets greater than 10%, you end up oversampling your population. You don't want to do that. The last condition here. Now, with proportions, you're typically used to large counts. But here's the thing. When you're dealing with average height, there's not going to necessarily be large counts here because large counts is based on success and failure. You can't really succeed or fail based on height, even though some people would argue that, if you're too short, then that's a failure, or if you're too tall, then that's a failure. No, we don't live in that type of world here when we're dealing with means. So what is our condition? we're going to go with what's called the large sample / normal. What does that mean? You typically want a sample size that's going to be greater than 30, greater than or equal to 30, or your sample is a normal distribution. You'll typically, you can prove that with a histogram. You can prove that with a dot plot. Typically, we want to do, sample sizes. If possible, you want to go a little bit bigger than 30 because, larger sample sizes are better. So for the sake of what we're doing, you'll notice I went with 36. That is larger than 30. So that is checked. Again, if it was less than 30, then you would just take all of your samples and you would make a nice little histogram here. Or maybe you'd make a dot plot. And then as long as either of them look, I hate to say normal-ish, but as long as there's not like a super skew or any super outliers, we usually say that's okay. Again, because it's a smaller sample size. So again, the three conditions, you got random, 10%, and the large sample / normal. Now let's calculate the standard deviation of our sampling distribution here. We know what it is for our population. We know it's 3 inches. Our sample size in this case, we went with 36. So I'm going to plug in 36 at the bottom here. We want the square root of 36. You almost notice it's going to give you a nice easy number here. 3 divided by 6 equals 0.5. So the standard deviation of my sampling distribution is going to be ½ an inch. So down below, I'm going to create my sampling distribution. Now the mean of that sampling distribution is going to remain 69 inches. My standard deviation is going to go up by ½ an inch. 69.5. 70. We're going to go down ½ an inch here. 68.5. 68. And then I'm going to put my z-scores down below too. It's good to have those z-scores. I usually like to go out 2 standard deviations, as a lot of you know. And then I'm going to establish my empirical rule up here. 68% of my data falls within 1 standard deviation. 95 falls within 2. And then I just account for the tails over here, that 2.5% on each tail. Some teachers will tell you to go out 3 standard deviations. I'm not going to argue with that. It's not a bad idea, but I like to go out 2. So what does this mean? What did I just establish here? What I just established is if I go out and ask 36 random U.S. males, I get their heights and I find the average. This is going to represent all the averages I could get based on this population if I do a sample size of 36. So I could go out there. I could, randomly sample 36 males. I could get 68 as my average height. I could also get 69, spot on. I could get 68.5. As you can see, I can get so many different statistics from this population. Tons of them. That's what all these X bars represent. That represents all the possible statistics I could get. Now I can sit here and draw X bars all day because frankly, it's nearly infinite because this is continuous data. It's not discrete in this case. I could literally get I could get infinite amount of data. But here's what we want to take note of. If we do a sample size of 36, chances are, again, because we got our standard deviation of 0.5. We got that from taking our population standard deviation of 3, dividing it by the square root of 36. So what that tells me is that if I do a random sample of all U.S. males, I record their heights, get the average of height of my sample, right, of my sample distribution, right, I get all these, my sampling distribution. 68% of the time, I could expect the average height of my sample to be 68.5 to 69.5 inches. And I'm going to write that out here. If I perform, well, boy, I want to write that out a little better. If I perform, see, I sacrificed the better stylus because it makes too much noise, so I'm going with this one instead, and I think I'm paying the price for it. Try one more time. If I perform a simple random sample of 36 U.S. males. I could say 68% of the time I'd expect an average of 68.5 to 69.5 inches. Also, I could think on the high end here. I could think if I look over here, these are statistics I'm less likely to get because as you can see, there are less statistics on this end of the distribution. There's only 2.5%. I could also go on the limb here and say, same thing, if I perform, I'm going to do these quotation marks, if I perform a simple random sample of 36 U.S. males, I'd expect an average height of 70 inches or more, 2.5% of the time. Ideally, what does that mean? That means it's fairly really unlikely, as a matter of fact, that if I get a simple random sample of 36 U.S. males, I'm going to get an average height of 70 inches or more. That really should not be happening. It could, like 2.5% of the time, but it really shouldn't be happening. Likewise, I can even go on this end. If I do a random sample of 36 U.S. males, find the average of that sample of 36 U.S. males, I should be getting an average height of 68 inches or less, only about 2.5% of the time. Why? Because less, like 2.5% of all possible statistics from this population should result in 68 inches or less. Because again, this represents all the possible averages I could get from that sample. That's what a sampling distribution is. Represents all the possible averages you could get from a sample from a given population. So let's try another one here. We're going to go with average U.S. income. Now, I started out with data that was a little bit more accurate, but I sacrificed that for the sake of being able to draw a better distribution. So 43,000 isn't entirely accurate. I actually got this from some county data. But the standard deviation I thought was interesting too. The average U.S. income is $43,000. Standard deviation we went with was $30,000. Might seem awfully high, but you also want to remember, right? Income, it's kind of a bit of a disparity. People can make a lot more than $43,000. They can make less, So I mean, it kind of, really spreads it out. You'd almost expect the distribution to look very, it'd be a bit out there. But let's see, we're going to do a simple random sample of 100 people. So if we randomly sampled 100 people in the United States, ask them their incomes, what averages would we expect? We're going to look into that. First, we're going to check our conditions. First of all, we want to make sure we're basing this on a random sample. Are we? Yes, I said it's random. 10% condition. All right. You want to check, is 100 people greater? Is it less than or equal to 10% of all U.S. citizens, we'll say? I think that's very safe to say here, so we're going to go with that. And then the last condition. Again, this is the normal/large sample. If I wanted to, I could draw, a histogram of what these samples would look like, but we're just going to go with the large sample condition here. So we're going to go with large/normal. In this case, 100 is greater than or equal to 30. So I would not have to prove that a sample from this would give me something that looks somewhat normal. So I'm in good shape here. Standard deviation of my sampling distribution. That means the standard deviation of all the possible statistics I could get. Again, I used a nice easy number. I'm going to take $30,000 and divide that by the square root of my sample size, which in this case is 100. 100 is a nice easy number. It gives me 10 when I find the square root of that. They're not always going to be this easy, so if you run into a sample size that doesn't give you a perfect square root, that doesn't mean you did anything wrong. I just like doing this because it's easy. 3,000. So what does that mean? I'm going to establish my data down below here. $43,000 is the average that I would expect from all my statistics if I randomly sampled 100 US citizens and got their average income. $3,000 is my standard deviation, so I'm going to go up $3,000 in this direction, and then I'm going to go down $3,000 in this direction. So I'm going to go down to 40, and then 37 down here. My z-scores are always the same. 0, that means you're 0 standard deviations away from the mean because you're right on the mean. 1, 2, -1, -2, because you can have negative z-scores. That happens. Now, what does this mean? Let's break it down. So what that means is if I do a random sample of 100 US adults, average out the income of that sample, of that 100 people, I could get a statistic out here. I could get a statistic in here. I could get one here. Heck, I could even get one way out here. Not terribly likely, but it could happen. I could even get one way down here. Chances are I'm going to get one that's really close to the middle here because, as you can see, most of my statistics are fairly close to my average. So what observations can I make based on this? Well, again, I like to use my empirical rule here. I like to establish my 68, 95%. And then I like to go 2.5 in this direction. Now I can make some observations. I could say, based on my sampling distribution, if I did a random sample of 100 US adults, 68% of the time I'd expect to be getting an average income of $37,000 to $49,000. I could also say, like, hey, I can break it down. I love doing this. Break these into pieces, 34% here, 34% here, 13.5 here, 13.5 here. I could say that I'd expect 13.5% of the time I would get an average between $46,000 and $49,000. Why? Because in my sampling distribution, 13.5% of all possible statistics fall between $46,000 and $49,000. I could also say, hey, I'll get a little adventurous here. 47.5. Where'd that come from? I just added these. 47.5% of all possible averages based on a sample size of 100 will give me an average income of $37,000 to $43,000. And that's what a sampling distribution is. It represents all the possible averages you can get based on the sample size of your choice. Now watch what happens. I'm going to kind of get a little adventurous here. Say I change that sample size to 1,000. Or better yet, I'm going to make it easier. I'm going to go with 10,000. Why? Because now watch this. If I change this to 10,000, square root of 10,000 is 100. I get to cancel out 2 zeros. Now my standard deviation goes down to 300. So by making my sample size bigger, I get a smaller standard deviation. And that makes sense because when you get a larger sample, you would expect to get a bit close, expect to get closer to what the actual parameter is. Smaller sample size, less of a chance you get close to that parameter. So all I'm doing here is I'm just rewriting it. Doing some incorrect subtraction here. This is what happens when you do it in your head. Use a calculator, folks. So when my sample size gets bigger, my standard deviation gets smaller, which means I have a much better probability of getting really close to that parameter here. As you can see, now I'm really close here. 68% of the time, if I increase my sample size to what I use here, 10,000, then 68% of the time, I'll get an average from $42,700 to $43,300. That's a lot closer to what the actual parameter is, $43,000. So as we know in statistics, it's good to have a good sample size. If you want a big sample size, that's good. You just want it to be less than 10% of your population, because then you run the risk of oversampling. So let's wrap this up. Let's go back and take a look at what we just went over today. A sampling distribution represents all the possible statistics you could get from a population. The average of all those statistics will give you the parameter for that population, the thing you're ultimately looking for. The standard deviation of your sample, you take the standard deviation of your parameter, divide by the square root of your sample size. And then you can figure out what percent, how close you can get to that actual parameter. Using a normal distribution, because sampling distributions are normal when our three conditions are met. If it's based on random samples, if it's based on samples that are less than 10% of our population, and if our samples are greater than 30, or they're somewhat normal when we draw them as a histogram. And we also noticed that when we make our sample sizes bigger, we're much more likely to get a statistic that's close to that true parameter. All right, good luck, and hopefully this helps you with sampling distributions based on means.